The first part of our 5 notes on the trapezoid rule is dedicated to Daisy Stinson for your remarkable improvement in the class. It definitely has not escaped my notice, and I hope that your upward momentum continues and brings you all the way to a 4 or 5 on the AP test. So, trapezoid rule, let's go ahead and derive it, and let's take for instance the graph of this generic curve, f of x. Suppose we want to find the area under that curve from A to B. We could split up that area into n subintervals, like we've done in the past. N just being the number of partitions, and in this generic example I've got 4. Now, we began problems like these by using rectangles, and the more rectangles you have, the more accurate area you have. But the problem is, with rectangles, since the top of a rectangle is flat, you end up with a lot of error, or in this case, a lot of gaps, not giving us the exact area. If we use trapezoids, however, the beauty of trapezoids is they have a diagonal side, or they can have a diagonal side, and so that helps to minimize a lot of the error. So if you compare these trapezoids in here with the rectangles, you can see with the rectangles there was a lot of underestimating, whereas with the trapezoid we reduced a lot of that error. There was still some, but a lot of it gets reduced out. So to use the trapezoid rule, we would first need to remember what the area of a trapezoid is, which is 1/2 base 1 plus base 2 times the height. Next, we want to notice that the height of each trapezoid is the same and is the change in x for each interval. So we're used to seeing trapezoids like this, which is why this one side is called the height, because we're used to seeing trapezoids like this where their two parallel sides are horizontal. The trapezoids that we have under this graph have been flipped up onto their side. So you can see this one here is sort of an enlargement of what this trapezoid would look like. So since it's flipped on its side, the height then is actually this horizontal distance at the bottom, and so for each of these trapezoids it's the same, and it's the change between all the x values. Next thing I want you to notice is that, again, when you're seeing a trapezoid in its standard position, it has two parallel sides of different lengths, and we call those bases because when you have it in standard position they're horizontal, and base 1 is just one of the sides, base 2 is the other side of different length. Now again, these trapezoids have been flipped up onto their side, so now those two bases are vertical. So you can see if I look over to this trapezoid here, to find the bases I would need to find the distance between the x-axis and the curve itself. So looking at the above graph, the heights are the changes in x, or our delta x. And since I'm cutting the region into n subintervals, typically we like to just split it evenly. So we take the entire distance between a and b, which is b minus a, and divide it by n to give us an equal distance. And so that ends up being our height for each trapezoid, is the change in x, which will be b minus a over n. Then, to find the length of each base, you would take all your x values at the end of each subinterval. So let's just give those names. So for this example, let's just call this x1, x2, and x3. These are all the x values at the end of each subinterval. To find the basis of the trapezoid, you take that x value, you plug it into the function, which is what's making this curve, and that will tell you how high these bases are going. So I have a base of f of a, f of x1, f of x2, and so on. Now, to find the area under the curve, using this approximation, I just find the area of each trapezoid and then add them together. So I'll start with the first trapezoid, which I bolded with the color blue. So you can see the height, well, the formula would be 1/2 times base 1, which is f of a, plus base 2, which is f of x1, times the height, which we'll just call h. So there's the area of this trapezoid that I have outlined in blue. Next, I need to find the area of the second trapezoid, which I have outlined in green. And it's the same formula, 1/2 times the first base, which is f of x1. And if you'll notice, f of x1 was used twice. It was the right base for the first trapezoid, and now it's going to be the left base for the second trapezoid. And then I multiply the sum of those bases by, again, the same height, h. For the third trapezoid, which I now have outlined in yellow, same formula. So I do 1/2, just like before. The first base, which is f of x2, and again, notice f of x2 is being used twice. It was the right base for the second trapezoid, now it's the left base for the third trapezoid. And then plus f of x3, which is the second base, times, again, the same height, which we're just calling h. Last but not least, we have the area of the trapezoid highlighted in red. And so again, it's 1/2 times the first base, which is f of x3, times the second base, which is f of b, times the same height, h. So what I'm going to do now is simply add together each trapezoid area. But notice that they each have a 1/2 in common, and they each have h in common. So as I add them up, I'm going to factor those common values out. So notice here on the left, I've got 1/2 and h factored out, and then I'm just adding together all of the bases. So I'm adding f of a, f of x1 twice, f of x2 twice, f of x3 twice, and then f of b. So to emphasize, I have some like terms, and we talked about this when we were finding the area of each trapezoid. F of x1 was used twice for the first and second trapezoid. F of x2 was used twice for the second and third trapezoid. And f of x3 was used twice for the third and fourth trapezoid. So we can combine those like terms together. And I have, again, the 1/2 h on the outside. I have the f of a from before, and then I just combine these together. There's two of them, so that's 2 f of x1s, 2 f of x2s, and 2 f of x3s. So now I want to generalize that for any number of partitions. So my example here had 4 partitions, but I want to generalize that for any number of partitions. So I'll just go ahead and combine the 1/2 h as h over 2. The f of a would still be the same. 2 times f of x1, 2 times f of x2, and then I just sort of included however many others there are up until the second to last one is doubled, and then the very last one is f of b. And then just again to recall that the height is going to be the same for every subinterval, and it will equal b minus a, which is the distance from a to b, divided by n, which is the number of subintervals. Okay, so you have to notice something very important here. The f values at all the intermediate x's, that is for all the x's that are in between a and b, those are all doubled because they were each used for 2 different trapezoids. So again, all the intermediate, or all the f values of the intermediate x's are all doubled up until the second to last one, because they're all used for 2 trapezoids, whereas the endpoints, or the f values at the endpoints, the f of a and the f of b, are only used once, because f of a was the left base for the first trapezoid, and there was nothing to the left of that, so that base was only used once, and f of b was the right base on the last trapezoid, so there was nothing else to the right of that, so it was only used once. Whereas all the intermediate ones are used twice. This will help you in memorizing this formula. So here you have it. You need to memorize it, and now we're going to use it in a couple of examples. So for this first example, we're given this integral, and we're asked to use the trapezoid rule to approximate the value of this integral. And we're asked to use 4 trapezoids, or break it into 4 subintervals. So it helps if you can kind of look at the graph. So here's the graph of x squared, and again, I'm only looking between 0 and 2. And then I notice that I need to split it into 4 subintervals. So if I do that, and I notice that the distance from a to b is going to be 2, because a is 0 and b is 2. And then I'm going to divide that into 4 equal parts, so the distance of each subinterval will be a half. So I'm going to go ahead and split this into halves. and draw in the 4 trapezoids. And then I'm going to recall the trapezoid rule. I already figured out my value of h, which turned out to be 1/2, so I plug that in here. So I have 1/2 divided by 2. My first x value is 0, so I'm going to plug 0 into the function. My second x value is 0.5, and I'm going to take 2 f values at 0.5 based on the rule, and so on and so forth. So 1/2 divided by 2 gives me 1/4. F of 0 turns out to be 0. F of 0.5, if you look here, turns out to be 0.25, but then I have to double it, and then that becomes 0.5. F of 1 becomes 1, and then I have to double that, so I get 2. F of 1.5 becomes 2.25, but then I have to double that to get 4.5. And then for f of 2, I only use it once because it's the last base, and f of 2 is 4. So add that all up, and I get this approximate value of 2.75. Now, that's the answer that we have to what the question was asking, but let's think about that in terms of the actual area. A lot of times AP tests are going to ask you if your estimate is over or under the actual value. Well, let's take a look at our picture here. So my curve, x squared, is what we call concave up. So, and if you were to zoom in here, you would see that the trapezoid edge is straight, but the curve is concave up, so it dips slightly below the trapezoid edge. So because our curve is concave up, our estimate here for the trapezoid will be over or a little bit above the actual value, because the top of each of these trapezoids is a little bit over or a little bit above the actual curve. So to see if we're right, to check our answer, we could actually just calculate this integral. This integral is one that we can find the actual value of. Turns out that it's 8/3, which is about 2 2/3, or 2.6 repeating. So we can see that our value is a very close approximation, but it was in fact a little bit over the actual value. And that's again because our curve was concave up. For our second example, we're going to use the trapezoid rule on what you might call a discrete situation, or one where an equation is not given. So in this scenario here, we would not be able to use an integral to find this area. So the situation is, you're the fish and game warden of your township, and you're responsible for stocking the town pond with fish before fishing season. The average depth of the pond is 20 feet. Using a scaled map, you measure the distances across the pond at 200-foot intervals, as shown here. And then you're being asked to use the trapezoid rule to estimate the volume of the pond. Okay, so let's notice we're trying to find a volume. That implies 3 dimensions. The third dimension in this case is going to be that depth of 20 feet. So what we're going to need to do is find the area of the surface of the pond. So this here is the surface of the pond. We need to find all that area and then multiply it by the depth to get the volume. So notice, according to the picture we have, there are 8 subintervals. One of them is here, 2, 3, 4, 5, 6, 7, and 8. Secondly, notice that the height of each trapezoid is 200 feet. We could see that either from at the bottom where it mentions the vertical spacing. We could also read it from the problem above where it told us that we measured distances at 200-foot intervals. So that means each distance between measurements was 200 feet. And so that'll be the height of our trapezoid. So if you look at our trapezoid, these are now trapezoids like in standard form. The height is going up and down, and the bases are going left to right. So the bases, like I mentioned, are going left to right, and they're the distances that were measured across the pond. The first one being at 520, 800, 1000, 1140, 1160, 1110, and 860. Those are going to be the bases of each trapezoid. And technically, we do have a left endpoint where that base was 0, and a right endpoint where that base was also 0. So we recall the trapezoid rule. We recall that h was 200, that's the vertical spacing, and so we plug everything in. So I get 200 divided by 2. My first base is 0, because that was this value here. My second base is 520, and I'm going to double that one because these are all intermediate values, and so they all get doubled. So I have two 800s, two 1000s, and so on. And then my last final base is 0. So I simplify that a little bit. 200 over 2 becomes 100, and then all these values doubled are right here. Add that all up, multiply by 100, and you get 1,318,000. Okay, now that was the area of the surface of the pond. What we're being asked to find is the volume. So to find the volume of the pond, you just take the area of the surface that we just found and multiply that by its depth, which is 20 feet, which was mentioned above in the problem. So multiplying that, we end up with a volume of 26,360,000 feet cubed. That would be the total volume in the pond. Now, in your outline for notes, you actually have a couple other parts to this problem that I want you to solve as you tries, and we'll discuss them in class. So there was our final answer for the second example, and I'll see you in class.